Hello everyone, we're going to present to you Doc Design 2.0, an automated database design solution for document stores using multi-criteria optimization. So when it comes to schema design problem in document stores, the main thing is, as opposed to traditional relational database management systems, denormalization is encouraged. And you have multiple choices in a document store in terms of nesting, refactoring, and even the ability to have heterogeneous collections. So if you take a small example of authors and books and a many-to-many relationships between these two, for a relational database management system, you would have two separate tables for authors and books, and a bridge table in the middle to have to support the many-to-many relationship. So with the normalization, you end up with this solution. However, in a document store, we could come up at least 7 solutions as I have given here. For example, you can have books as the top level collection and the authors can be embedded, or the other way around, where the authors are the top level collection and the books are embedded. And we can also have redundantly embedding both books inside the authors and authors inside the books. And we have then can have references of the authors inside the book, and authors can have only references for the book that they have written, or you can have references of both ends, like in the sixth solution. Finally, you can also have a reification solution similar to the third normal form in a relational database management system. So out of these 7 designs, which one is best suited for you? So making this decision is unfortunately not trivial. However, this design affects the performance of your queries. Not only the queries, there are 4 main factors that we concern that is affected by the design. One is the storage size. If you have redundant data, the storage size increases. However, the query performance might increase because the reduction of the joins or the complexity of the queries. Then the complexity of the documents is also important. So you could have multiple nesting levels, which might not be ideal for a particular user. Finally, we have the heterogeneity within the collections, where heterogeneous documents can be within the same collection. For example, the authors and the books can be in the same collection in a document, so which is a perfectly valid design. However, how do we choose the best design for a document? So currently, this design process has been carried out in a rule-based ad hoc manner. If you see a particular data access pattern, you would try to apply this rule and design the data accordingly. So to further illustrate this point, we gave a questionnaire with to the set of participants with 2 entities and 1 relationship, similar to what we just presented between authors and the books, and ask them how many designs that they could come up with for this particular scenario for a document store. So only 3 designs were decided by 63% of the participants. So you actually missed more than half the designs by most of the participants. And only 9% managed to find the optimal design. And out of all the participants, 40% gets the 4th best design as the optimal. So we can clearly see that there is a complexity of finding the best design for a document store for a particular given use case. So this gets more complex when you increase the number of entities and the relationships, where the possible designs grows exponentially with the number of relationships. Therefore, our solution, this is the workflow of our solution, where you have, let's say, a typical document store like MongoDB, and you have a workload or the set of queries that you want to explore. And we have the optimization criteria, the storage space, the degree of heterogeneity, the document depth, and the query performance. Then we assume that we have the old schema that we have in the database. We use a canonical representation based on hypergraphs to represent the schema. And then using a set of transformations, we can come up with the alternate designs, which becomes our solution space. And then we have the objective functions derived from these the criteria that we want to optimize. And here we do multi-criteria optimization using a cost model and calculations of the storage size and the heterogeneity and document depth through the canonical representation itself. And finally, we have optimal set of schemas that can be used back in the document store to apply this new physical design. So let me show you a demonstration of our Doc Design 2.0. So here you can see the interface of Doc Design 2.0. So the main two parameters that we want to include here is the entity relationship and the query workload, which are given in the JSON format, which is specific to our solution. So if we quickly look at the entity relationship, here we have the entities, their attributes, and the number of instances of the entities. For example, in this case, we have the user and 500,000 user instances, and the user ID has a size of 4, and the user fname is a varchar of 20 bytes. Then when it comes to the workload, it is a design independent query that is given on the entity relationships that we already given. So moreover, like in the entity relationship, we also have the relationships between the entities. For example, between the region ID and the user ID, there is a one-to-many relationship. So when coming back to the workload, so we give the selection attribute plus the projections that we want to do through the selections and the relative frequency of each of the queries. So we have input all the 11 queries here. And then once we input these values, we can also select the objective weight by giving relative importance between the different objectives or giving the exact values to the objectives that we are want to optimize, the depth, heterogeneity, the query performance, and the storage size. Plus, we can give the number of iterations that we wanted to do the multi-criteria optimization. So once we press it, what happens is when I say 2 iterations, it will wait for 2 consecutive shots in the shotgun hill climbing algorithm to have the global minimum, and give it, once we reach that threshold, it will give the optimal solution. So the higher the number of iterations we give, the better the result would be, plus the more longer it would take. So here we can see it gives a relative estimate of the query cost, the storage size estimation, the average heterogeneity, and the average depth. So here in case there would be average depth of 3. And here you can also have the optimal design presented to you in JSON. For example, here you can see the collection of products. It's separated from the other entities and so on. So as you can see, with quite of ease, we can find the optimal solution using doc design and multi-criteria optimization. For example, if you run for a longer time, it's highly likely you will have a better solution than the solution that is presented here. And to make things easier for the end user, we also have given solutions where you can generate the entity relationships by the end user itself to generate the JSON that we want, plus to generate the workload as well. So thank you very much. I hope to see you in the actual demonstration. Thank you very much.